All right, so once we decide on what our assumption is and what we're trying to test, we want to set up a sampling distribution. We want to model the probability of taking this sample and seeing how it varies, right? Every time we take a sample, we're going to get a different answer. We're going to ask different people. We're going to have different problems. Like maybe a problem is a little kitten that's not a kitten anymore, but still sometimes behaves like one. All right. And we got that randomness, and we're curious how unlucky were we, or maybe the assumption was incorrect. So in this step, we're going to have to check the central limit theorem to make sure that we can even use a sampling distribution. And then we're going to set up the sampling distribution of proportions and calculate the test statistic. Remember, test statistic is that z value, which says how many standard deviations above or below the mean are we? Okay. So you might say, central limit theorem, what was that? We talked about it in two ways in Unit 6. So on page 1 of Unit 6, this was a central limit theorem. This one right here was for means. We use this for sampling distributions of means. And there were 3 conditions that we checked. There was also one in Unit 6 near the bottom, somewhere, for sampling distributions of proportions. It's taking a long time for this document to load. All right, so this is one of the later things right here. So this is the other thing that we're going to have to check. All right, so find this in your Unit 6 notes. These are conditions we have to check. All right, and this is where that standard deviate, that mean and that standard error comes from for that sampling distribution, those numbers that we used in the first video right here. So for proportions, what are the 3? And again, there's another one for means. For proportions, we need independence. And independence a lot of times means sample less than 10% of the population. So independence, less than 10% of population will give it to us. It's not the only way to get independence, but it's one way. The second thing we have to test is randomization. Samples are randomly chosen. And the last thing we have to test is a success failure condition. All right, we need at least 10 of each. At least 10 successes on average and failures. And we tested that by looking at n times p and n times q, both be at least 10. Right? The average number of successes, if p is the probability of success, is going to be how many are there? What's the probability? Multiply them together. And same with NQ. All right. So in our coin flipping example, independence, yes, every coin flip is independent of the one before it. Randomization, yep, it is a random event. We are flipping it 50 times, which means we have expected number of 25 heads and 25 tails, which satisfies the success failure condition as well. Okay, so we had all of these for that first page, even though we didn't explicitly test them. And now we're going to move on to step 3. So step 3 said, set up the sampling distribution of proportions and calculate the test statistic. Sampling distribution of proportions is normally distributed with mean p. We don't know p. We're assuming p to be that p naught, that number. We're assuming from the null hypothesis. With standard deviation, that's going to be, again, that assumed probability, p naught, q naught, n. And this whole thing is under the square root. All right. So that's our sampling distribution. The assumed population proportion and then use that assumed population proportion. Again, this is the assumption from our null hypothesis. Null hypothesis is the status quo, is the assumption. If everything is working as intended, if in the null hypothesis is correct, these are the assumptions that we use to model this sampling distribution. And then the test statistic is just what we've been doing the whole quarter for converting things to standard normal. If something is standard normal, then the test statistic is always just the value minus the mean divided by the standard deviation. This is what it is in general. Well, when we're looking at proportions, it's always going to be our sample proportion, the mean of our sampling distribution, right? The mean of our sampling distribution is P naught, divided by the standard deviation of our sampling distribution, which is again the square root of P naught Q naught over N. Right, so this is just the mean. And this is just the standard deviation. That's where these come from. So in general, this top formula is a little easier to remember. How far are we from the mean? Standardize that by dividing by the standard deviation. But if you want a big messy formula, which I do not recommend, here's this one. Our specific case, this is what our mean is, and this is what our standard deviation is for our sampling distribution. So let's work on step 2 and step 3 for 2 examples. And there's a little error in the notes. It accidentally copied down the problem from the last video, so we just edited it a little bit. Set up the sampling distribution and calculate the test statistic. Make sure to check the central limit theorem. So central limit theorem wanted us to check independence, wanted us to check randomization, and wanted us to check the success failure condition. We have to check all of these before we even set up a sampling distribution. If we don't have all of these, we can't set up a sampling distribution. Since we're looking at proportions, we'll use the proportion conditions. But if we had to look at means, we'd have to go back into unit 6 and check the central limit theorem for means. All right. For sampling distribution of means. Okay, so the old antacid provided relief for 70% who used it. Pharmaceutical company has a new drug they want to test to see if it's more effective. All right. So this one, I mean, we're testing it on less than 10% of the population. It doesn't tell us explicitly, but I mean, there's no way that we're actually going to do a test on more than 10% of the population of people in whatever the world. So we do have independence here, right? Less than 10% of population is what we're testing. Randomization, it doesn't tell us this, but we can assume this. Assume that we're doing things randomly. And success failure, well, N is 50. Again, this slightly bugged problem, missing a little bit of information, but I'll provide you a little extra. Assume that N is 50. So what's N times P? And again, P is 70%. We'll have to calculate these. N times P is 50 times 70%. Where's my calculator? 50 times 70%. On average, there's 35 successes. And on average, you do the same calculation with Q. There's 15 failures. So we have to have, right? This is bigger than or equal to 10. And this is also bigger than or equal to 10. So we have all 3 requirements of the central limit theorem. So we can model this with a sampling distribution and calculate the test statistic. So p hat going to be normally distributed with mean. Let's use this information from up here, right? The mean of the sampling distribution here is going to be p naught from that null hypothesis, that assumption or status quo on that p naught, that null hypothesis in the last video, to be 70%. All right. And the standard error, well, we're going to have to go off to the side and calculate that. Right, the standard error is the square root of p naught q naught over n. The square root of 0.7 times 0.3 divided by n, which is 50. Our standard error for the sampling distribution, square root of 0.7 times 0.3 divided by 50, which is 0.0648. So on average, assuming the null hypothesis is correct, assuming that this new drug is 70% effective, then when we, do a sample, take a sample, do a test, on average, 70% of the people will have relief, plus or minus about 6.5%. The empirical rule for normal distribution says about 68% of the time, 68% of the experiments will be between one standard deviation below the mean, one standard deviation above the mean. So about 64% and 76% on average success rate every time we do this experiment. Okay, so that's how we expect p hat to behave. It's going to be random, right? Every time we do this experiment, it's going to be random, but it's going to be a normal random variable given our assumption. Okay, so we also have to calculate the test statistic to say in our situation, so we did a little experiment ourselves and said that p hat was 75%. So we're assuming that it's 70%, and in ours, we found it to be 75%. How unlikely is that? How many standard deviations away from the mean is that? Okay. And again, we're not doing the full hypothesis testing yet. Just looking at these specific steps. And to figure out how unlikely that is, we look at the z value. Okay, known as our test statistic. So our test statistic is our p hat, this guy up here. It's our p hat, just 75%. How far away is that from our assumption? Just 70%. Divide that by the standard error, which is 0.0648. Our test statistic is this fraction. Make sure to use parentheses. 0.75 minus 0.7 divided by 0.0648. Is that it? Yeah. It's about 0.7716. Remember, this is not a percent. Z values have to do with standard deviations. How many standard deviations above or below the mean are we? We're not even one standard deviation above the mean. We're actually pretty close to the standard deviation, right? Our experiment gave us 75% success, and the assumption was 70%, and the standard deviation was about 6.5%. So we're not even one standard deviation away from the mean. This is pretty close to what was expected with the old drug. We're not going to do much more with that in this video, but in the future video, we'll talk about p-values and whether this is enough evidence to show that this new drug is better or not. It's not enough evidence. All right. But that's our test statistic. So right here is our test statistic. And here is our sampling distribution. All right, so I recommend that you pause the video, try to replicate this for part B. And again, we're crossing out part C. All right. All right, let's check the central limit theorem, see if we can set this up with a sampling distribution. So independence, are we sampling less than 10% of the population? Well, the population's 1,500, we're sampling 56. All right, 56 out of 1,500 is less than 10% of the population, so we have independence. Okay, remember that this is our n right here. N is our sample size, not our population. This right here is population. We need to randomly select. And again, we can assume that we are doing so randomly. And the last thing is a success failure condition. What is our P naught? What is our assumed probability? The assumed probability is related to the null and alternative hypotheses, which is what we did in the last video to say that this was 80%. Our null hypothesis is that P is equal to 80%. We're assuming that the proportion is equal to this P naught, this 80%. All right, so success failure condition, going to look at n times P. Well, n times P is going to be 56 times 80%. Again, we don't know P, we're assuming P is about P naught. 56 times 80%, our expected number of successes is 44.8. Expected number of failures is n times Q, this times 20%. Ooh, very close, 11.2. But again, even though it's close, they're both bigger than 10. All right. So it's a close one here, but yes, we can use a central limit theorem. And just like before, we can set up our sampling distribution. P hat is normally distributed with mean P naught and standard deviation P naught Q naught over n. We'll go off to the side, calculate 0.8 times 0.2 divided by n, which is 56. Our standard error right here is a square root 0.8 times 0.2 divided by 56, or about 0.0535. Which means our sampling distribution, every time this company samples 56 cars, they're going to get a random number of cars that meet the emission standards. And that random number is normally distributed on average. If this assumption is true, 80% of those cars will meet the emission standards with a standard deviation of about 5%. On average, assuming our assumption is true, which is a big part of hypothesis tests, that assumption, every time we do this, it'll average, about 80% plus or minus 5%. Okay, that's our sampling distribution. And our test statistic is just going to be, what's our P hat? All right, in the last one, we just did P hat minus P naught divided by that standard error. We haven't calculated our P hat yet, right? In our situation, we tested 43 out of 56, or we tested 56, 43 were successful. That's our P hat. So in our situation, 76.79% were successful. 76.79 is our P hat. That's our P hat right there. So to find our test statistic, we take P hat, 0.7679, subtract it by the mean of our sampling distribution, which is 0.8, divide by the standard deviation of our sampling distribution, which is 0.0535. And our test statistic is going to be about that. So this minus the mean divided by the standard error, 0536, 0535. Our z value, it's negative, that's okay, is about negative 0.60. Which means we're half a standard deviation below the mean, about. Okay, so again, the test statistic is how many standard deviations above or below the mean are you? Well, in this company's situation, they tested 56 cars and 43 met it. That meant they were about 0.6 standard deviations below the mean, given the assumption is correct, that 80%. That 80% is the assumption. It's what we're trying to test. We'll tie that all together in future videos. But for now, this is steps 2 and 3 on setting up sampling distributions and finding test statistics. We'll finish up the method in the next video and then do some good problems tying it all together. Let me know if you have any questions, and good luck.